And I'm live. That is pretty nice. Today is 29th of October 2025, Wednesday. And with that, let's begin. We will be not solving, but we will be reading about greedy algorithms from, of course, our favorite comprehensive book, Introduction to Algorithms, CLRS. And yes, PDF. Here we go. Stop the video. Yep. Greedy algorithms. Yeah. We might not even need everything that we need that we will read in this, but I guess it would help in some way or another. And yeah, with that, let's just do this. Algorithms for, and yes, this thing is divided into sub chapters, and the goal would be to get to complete at least one subsection in one stream, but if that comes at the cost of quality of the learning, then we will opt for the quality and not for the main target of completing this thing. So yeah, that is the main thing, and let's just begin. Should and I can even do maybe in this in black dark mode. Should I cannot? No, my bad. Okay, anyways, algorithms for optimization problems typically go through a sequence of steps, okay, with a set of choices at each step. For many optimization problems, using dynamic programming to determine the best choice is overkill, and simpler, more efficient algorithms will do. Okay, so we don't always have to use dynamic programming for optimization problems. Makes sense. A greedy algorithm always makes the choice that looks best at the moment. That is, it makes a locally optimal choice in the hope that this choice leads to a globally optimal solution. That is like the whole greedy algorithm in one line. You make a locally optimal choice, which hopefully returns leads to the globally optimal choice. So, okay, this chapter explores optimization problems for which greedy algorithms provide optimal solutions. Okay, the kind of problems where greedy algorithms apply and work. Before reading this chapter, you should read about dynamic programming in chapter 14, particularly section 14.3. We did go through dynamic programming, so that is nice. Greedy algorithms do not always yield optimal solutions but for many problems they do. Yes, we cannot always apply the greedy algorithms. We first examine section 15.1, a simple but non-trivial problem. uh, the first section, and then a simple but non-trivial problem, the activity selection problem, for which a greedy algorithm efficiently computes an optimal solution. We will arrive at the greedy algorithm by first considering a dynamic programming approach, then showing that an optimal solution can result from always making greedy choices. And then they go about referring to different sections about how the chapter is going to be. This greedy method is quite powerful and works well for a wide range of problems. Later chapters will present many algorithms that you can view as applications of greedy method, including minimum spanning trees. Chapter 21, which is Dijkstra's algorithm for shortest path from the minimum spanning tree. Minimum spanning tree, a tree where we are making minimum number of steps to go from one edge to go from one leaf to the next leaf, I suppose. And then Dijkstra's algorithm for shortest paths from a single source. Yes, in which we are, and the time complexity in Dijkstra's algorithm is m log m. Yes, m log m. M because m into log m. M because we are going through each edge. M is the number of edges, and okay. So in this Kranz algorithm, we are going through each edge only once, and then for going through a particular edge, we have to sort the edges and find the one which has the smallest weight from the original source. So that makes sense. Yeah, these graphs is like greedy algorithm, and a greedy set covering heuristic shit. Heuristic is a fancy word. Minimum spanning tree algorithms furnish a classic example of greedy method. Although you can read this chapter and chapter 21 independently of each other, you might find it useful to read them together. Okay. Anyways, an act shit an activity selection problem. Okay, our first example is the problem of scheduling several competing activities that require exclusive use of a common resource with the goal of selecting a maximum size set selecting a maximum size set of mutually compatible activities. So we have a bunch of activities and they depend on a single source, like one unique source, and that source a common resource, and they require exclusive use of it. That is, when one activity is using that common resource, another activity cannot use it. So like CPU processing. Imagine that you are in charge of scheduling a conference room. Makes sense. You are presented with a set S which has values A1 to AN of n proposed activities that wish to reserve the conference room, and the room can serve only one activity that at a time. Makes sense. Each activity AI has a start time SI and a finish time FI. Okay, and if selected activities AI takes place during the half open time. This half open means this S1 is included and F1 is not included, or maybe the opposite. That is, F1 is inclusive, but S1 is not inclusive. The start time and the end time. One of them is included and the other one is not. Activities AI and JI are compatible if their intervals do not overlap. That is, SAI and JI are compatible if they do not overlap. Assume that if your staff needs time to change over the room from one activity to another, changeover time is built into the intervals. Okay, makes sense. In the activity selection problem, your goal is to select a maximum size subset of mutually compatible activities. Assume that the activities are sorted in monotonically increasing order of finish time. Okay, we have a bunch of activities. They require the conference room for them to be like engaged in, and we have to select or schedule these activities so that the room is being utilized as much as it could be, or no, that is not the thing that we are optimizing for. There could be one activity which spans the whole duration. We would not choose that. Instead, we would rather choose smaller activities to increase the count of activities in total. So yes, we want to increase the total number of activities conducted in the total duration. And we are saying that the activities are sorted in a non-descending order of their finish time, which is this thing. Okay. We will see later the advantage that this assumption provides. For example, consider the set of activities in figure 5.1, which is just this figure, the subset A3 and A9, A3 and A9 somewhere, and A11 consists of mutually compatible activities. That is not a maximum subset. However, since the subset this is larger, in fact, this is largest subset of mutually compatible activities, and another largest subset is this. Okay, shit, that does not make sense. What is this? It is not a maximum subset. Okay, in figure 15.1, which is figure 15.1, this is figure 15.1, and this is 15.1 something image, I guess. Okay, in this thing, figure 15.1, we have a subset A3, A9, and A11 consists of mutually compatible activities. That is where the times do not overlap. A3, A9, and A9, 11. Okay. A3, A9, and A11. Makes sense. 9 ends at 12 and the 11 one starts at 12. 9 starts at 8 and the third one ends at 6. So yes, they can be conducted. This is not a maximum subset, and by maximum subset, I would suppose they mean uh, the subset which has more elements and also the activities which are in that subset, they are mutually exclusive. Okay, that makes sense. And so they are saying even, I hope my voice is like still audible. Yes, it is audible, so that is nice. Okay, so A3, A9, and E11 are not mutually acceptable, mutually compatible, makes sense. And then A1, A4, A8, and A11 is this is larger, and in fact, this set is a largest. Okay, grammar largest subset of mutually compatible activities, and another largest subset is this. Okay, so they are defining largeness of a set based on the number of elements there are in a given set. So yes, and out of all the mutually exclusive sets that we can form out of these activities, 4 is the maximum size we can achieve. And they have given 4 different ways to choose these things. I think this is the largest because it has 4 elements, and all 4 of these activities are mutually exclusive according to this thing. Makes sense. And in fact, this thing is one of the largest subsets. And this one, A2, A4, A9, and A11 is another largest subset because it has 4 elements, 4 activities, which are also mutually exclusive. We will see how to solve this problem proceeding in several steps. Okay, first we will explore a dynamic programming solution in which you consider several choices when determining which subproblem to use in an optimal solution. Which subproblem to use in an optimal solution. We will then observe that you need to consider only one choice, the greedy choice, and that when you make the greedy choice, only one subproblem remains. Based on these observations, we will develop a recursive greedy algorithm to solve the activity selection problem. Finally, we will complete the process of developing a greedy solution by converting the recursive algorithm to an iterative one, although the steps we go through in this section are slightly more involved than is typical when developing a greedy algorithm. They illustrate the relationship between greedy algorithms and dynamic programming. Okay, so they are saying we are going to go through a whole cycle of things. So for the problem, first of all, we will go through a dynamic programming solution, right? So for the problem, we will define dynamic programming, and when we apply a dynamic programming solution in a dynamic programming mm, solution, like in a solution in an algorithm which is using dynamic programming, we have choices, and depend these choices lead to subproblems, right? Depending on what choice we make, we will get a bunch of subproblems, and among these subproblems, we find the one which has the best value and then incorporate, and then we see which choice led to that like very good subproblem which was giving us the optimal value, and then we go with that choice. So, and then they are saying if choice is always greedy, if the choice is always greedy, then strip out the DP part. I messed up the spelling. Strip out the DP part and Just simply apply the algorithm. Makes sense. And that actually makes sense. And now we'll see how to go through this. Okay, cool. That is even cooler. The optimal substructure of activity selection problem. Let's verify that the activity selection problem exhibits optimal substructure. Let's verify that the activity selection problem exhibits optimal substructure. Shit, yes, there has to be optimal substructure, which means for the main problem to be solved, we need optimal solution for the sub problems that it depends on. Makes it denote by Sij the set of activities that start after AI. Denote by Sij the set of activities that start after AI. Ij. Okay. Denote by Sij the set of activities that start after AI finishes and that finish before activity EJ starts. Okay, so Sij is the set of all the activities with which uh, this current activity can go with, like with which the activities which are the activities which do not overlap with the interval ij. Makes sense. Okay, that is these activities start after aij and eij finishes start after aij finishes and then finish before aj starts. Start after aij finishes and end finish before aj starts. Okay, okay. Suppose that you want to find a maximum set of mutually compatible activities in Sij. Mutually compatible activities, that is, they which activities do not overlap. And suppose further that the maximum set is Aij. Okay, sure. I am still not very clear about this definition of Sij. It is yes, denoted by Sij, the set of activities that start after activity AI. Okay, so we are considering two activities. Okay, the ith activity in Sij and the jth activity. And we, man, if I shit, this thing won't work here. Yeah, the browser page is protected. Pay for you. Shit. Yes, I cannot make this dark theme. And suppose further that such a maximum activity is set to Aij. So we are considering the ith activity and the jth activity, and Sij is denoting the set of activities which start after the ith activity. So for example, here if we do S2 3 S2 3, let's say, then all the activities which start after 5 or on 5, that would be this activity from 6 till 11. Okay, and all the activities which end before the third activity begins, and that is nothing. All the activities start after the third activity begins or end after the third activity begins. Okay, and suppose further, but I don't know why do they need something like this strange symbolism. Suppose that you want to find a maximum set of mutually compatible activities in SIJ. Okay. And suppose further that such a maximum set is Aij, okay, which includes some activity in AK and some activity AK. By including AK in an optimal solution, you are left with two subproblems finding mutually compatible activities in the set SIK, because we have included the kth activity. Okay, activities that start after AI, activities that start after AI finishes, and activities that end before K starts. Okay, and I is the activity which ends before AK K begins, ends before AK ends. So AI, yeah, AI ends before AK begins, before AK ends. So if there is an activity which starts after AI ends, AK ends, hmm, then that is not mutually exclusive with this, but that is not how we are defining Sij. Anyways, activities that start after AI finishes and that finish before activity AK starts, and finding mutually compatible activities in the set. Okay, in the set SKJ, activities that start after activity EK finishes and that finish before activity AJ starts. Okay, this is just going above. Hello, yes, we are doing some scheduling. Hello, good afternoon. Some greedy algorithm, and they maybe I'm stupid, which I think I am. Uh, This seems to be like there are very many variables here. They are defining this Sij, which I don't get. Like, why do they need this strange symbol? Sij is a set of activities which start after AI ends and begin before AJ starts. Okay. Anyways, and then we are saying we are looking for the maximum set of mutually compatible activities in Sij, and we are calling that set Aij, which includes some activity AK. By including AK in an optimal solution, you are left with two subproblems: choosing K with I and choosing K with J, Skj and Sik. Let Aik, sh- shit, let Aik equals Aij. Okay, shit. I guess we should spend a little more time on this definition Sij, right? This is kind of crazy. Sij. Sij denotes the set of activities that start after AI finishes, and K after AI finishes, and that finish before AJ starts. Okay. So we have a number line with time like going like this from 0 till n, and we have an activity, ith activity, which starts at some point and ends at some point, and we have our jth activity, which starts somewhere and ends somewhere, and we are saying Sij is the set of activities which start after AI finishes. Like, okay, all the activities in this range, and all the activities in this range, that is the activities which finish before AJ starts. So not exactly on this point, but 1 minus this point where AJ starts. Okay, why do we need all of these activities? Shit, this is a set of all the activities which are, right, okay, I can take up these activities. I can pair up these activities with this and some activities with this makes sense, I would say. But like, why do we even want something like this? And what if the order of I and J was reversed? If we had J before and I later on. If we had like J here and then I was later on, maybe not even overlapping, then activities that start after I and activities that end before J starts, like this. Okay, and this looks nice, but I could have started here, in which case we cannot pair up these activities with this. But one thing that is common in both the things is we can pair up all of these activities with I and all of these activities with the J activity, and that is nice. That is something we can do. So that is cool. Hello, have you solved CSS search and sorting problems? Nope, it has some scheduling problems. Yo, hello. I saw the solution yesterday and I think yes, it makes sense. It like I had to think about it quite a bit and it started to make sense. We were looking at like different distances. We have a number line here, numbers scattered in some way, another number line, numbers are scattered in some way, and then we are like with different values of j or I in the thing that you sent. I, when I was equal to 0, then the gap between the indices of these two elements is smallest, and then given this difference we are finding the one that is that gives us the smallest absolute difference. And since it is giving us the smallest absolute difference, then every other pair will have a absolute difference that is greater than the one that we got. And we are doing this for all possible differences, which is nice, which makes sense. And yeah, which does make sense. Shit. But yes, which problem? Yesterday there was a problem. And also, is there like a generic name for problems like this, or was this one simply a ad hoc problem? Because I have not seen a problem being solved like that. Like it was new, charming deals, shitty. Okay, I was wondering why you named this thing charm, and now makes sense why you named this charming deals. Yeah, this is the problem. Yeah. Nope. I didn't give the contest yesterday. It right now feels like right now is not the right time for the contest. This feels like that. And this was the problem. And I think it just takes time to get used to this because the solution that you gave is very, very new. I had like no idea about how this works, and that is new. And same thing happened when there was a problem in which we had to calculate, like there were two functions, fx and gx, and then the thing that we wanted to calculate, and these, yeah, and then we had a vector of values size, and size of this vector was n. And the thing that we had to calculate was summation of absolute difference of fi minus gi I going from 0 to n minus 1. And this is doable if we pre-calculate the values of these functions and sort them in order and sort at least just one of the vectors. Let's say we create two vectors, vector storing the values of fij for every I in the original vector, and ga vg vector which stores the values of this gi function when we give in the values in this original vector. And then we can sort one of these, and we can, let's say we sort vf sorted, and then we can go through vg. We will find, using lower bound or some function using binary search, we will be able to find where vg lies. Like we will find a element which is smaller than vg, the greatest element that is smaller than vg, and all the elements to the left are smaller. In vfs all the elements are smaller than vg, and on the right all the elements are smaller than current vgi. And we will also have a prefix for this, vfs prefix. And then it is easy, since we know what we need to calculate is vg into a bunch of multiplied by some number minus the sum of these, and then the sum of all of these numbers on the right, and vg I multiplied by how many numbers there are on the right. Mm, just do that. And this was difficult to understand. I like spent 5 days on this, and I guess the same thing goes here because this is very new. This is very new, very instructive. So yes, thank you for the solution. That was nice. Yeah, that is cool. That was cool. And on to greed and shit. This mm, and donation, no, this symbolism, this representation, what do you call it? Denotion. Denotation is kind of strange. Si and j. We have a set ai and aj. Sij is the set of all of these brown values. This Sij is the set of all of these values, and I don't know why we need them. Half of these can go with this one, and half of these, like in this range, can go with this one. Okay. And is there some theorem behind it? I mean, behind this one, uh, the question that you were seeing yesterday, or behind this summation of this thing? And this thing is just ad hoc, a trick, so that we can do something which generally would require n square time, but we are doing it in n log n time. Like for for me to understand this, I had to go to Reddit. I posted something, and some smart people gave me some understanding. I had to read a few things. I had to talk to ChatGPT. You were explaining, yep, this one. No, I don't think there is a theorem behind this, but there is a simpler version for this when we don't have one of these is a constant and is not a function, and that is much simpler to understand. like, or you don't even have to think about this as a function. Yes, you don't even have to think about this as a function. Yes, you don't even have to think about this as a function. Let's say you have a vector v, right, which has a bunch of values, and then you have a value x. X is a constant, and you need to calculate summation of I going from 0. This vector has n elements in total, I 0 to n minus 1, and you need to calculate absolute difference of vi minus x. And this is pretty simple. You can just do one pass through this vector and do absolute value for every vi minus x and add that to the response. Yeah, just sum them up. That would be your answer. But if this x is also changing with vi, that is, if you have two vectors, let's say v, let's call them x vector, which has n values, and a y vector, which also has n values, and shit, I miswrote. I messed up. Shit, yes, I messed up. My bad. This is wrong. I was lying here. Shit, this is wrong. This is not the thing. If this was the thing, then we can just do one pass because fi only depends on gi. So yes, that was wrong. The real difficulty was this. We had two summations, I going from 0 to n minus 1, and a summation j going from 0 to n minus 1, and we had to calculate xi minus yj. That is, you have a bunch of values here, bunch of values here, n values in total. This y0 is going to be paired up with every possible value of x, and we have to calculate the absolute difference when we have fixed this thing and we are varying the values in x. Then we have to do the same thing with y1, pair it up with all the other values, same with this, and till then y n minus 1. And this is n square time complexity. Yes, this is the n square time complexity. And in that case, we can do thing that I was talking about earlier here by using prefixes, by sorting one of the array, and yeah, using binary search internally. Yes, earlier it was I messed up. I messed up. Yeah, yeah, that was wrong. This is the thing. N square. Both of the things are varying. So, yeah. And I guess, yes, why was I even ranting about this thing? I think because this one is not having the same pattern in the sense of what is being talked about, but the similarity is that I don't get this. I didn't get that thing also at the start, but I just have to spend more time with not this thing, which Eric gave us yesterday on Discord. So that is nice. And now this Sij. Okay, okay, we can digest that Sij is this set, and some of these elements can go with I. Some of these activities can go with I activity, and some of these can go with J activity. So we have a choice. Okay. Then let's verify that the activity selection problem exhibits optimal substructure. Denote by Sij the set of activities. Yes, yes. That start after AI finishes and that finish before activity AJ starts. So some of these activities can go with AI and some with AJ. Suppose that you want to find a maximum set of mutually compatible activities in Sij. And suppose further that such a maximum set is Aij. Okay, the maximum set is Aij, maximum set where the activities do not overlap. which includes some activity AK. By including AK in an optimal solution, you are left with two subproblems. Okay, so AJ is a set of a bunch of activities which do not overlap, and among them we have chosen one activity AK. By including AK in an optimal solution, so we have all of these activities which can go, and all of these activities can go either with ith activity or with jth activity, which includes sum. By including AK in an optimal solution, you are left with two subproblems: finding mutually compatible activities in the set SIK, mutually compatible activities in set IK, activities that start after that that start after AI finishes and that finish before activity AK starts. Okay, and finding mutually. Okay, so this kth activity could be in this group, and if it is, then we are saying asking for an activity which starts after this thing ends, and since kth activity is also one of these activities, we are saying, uh, let's say kth activity starts at some point, and all the activities which are in this range, which like end before this point. Okay, okay, this is making some sense. There has to be some theorem or something because we take absolute of each number with the same bunch of numbers. What I was able to find out was there was one guy who said that whenever you want to calculate something like this, a double summation, you fix one of the values and binary search on the other set of values and find the answer for that fixed value, then move on, and then yeah, one by one iterate these fixed values and calculating the answer for one fixed value when you have a array of different array with which you have to pair up this fixed number, right? We can, let's say, choose one random number here, and this thing is fixed. You find the point where all the elements to the left are smaller and all the elements to right are bigger, and you also have a prefix for this. So what you will do is you will take the sum of all of these elements on the left and all of these elements on the right. From the elements on the right, you will subtract the sum of this xith element, and from all of these elements which are smaller, you will subtract this sum from xi multiplied by the count of these elements. That is what you do. So effectively you have found the answer when you fixed up xi. Then you just iterate through each x, and to find out answer for a particular xi, it takes you log n time, because this is already sorted, so you can easily in log time find out the point of separation. And since you already have a prefix, you can just calculate the sum in no time at all. So that is kind of nice. And this thing is not making a lot of sense, but let's just go with this for a while. EI finishes and that finish before the activity EK starts, and finding mutually compatible activities in the set SKJ activities that start after EK finishes and that end before AJ ends. Okay. Let AIK intersection. Shit. Let AIK equals intersection of EIK. That is the best set in this range I and K is the intersection of AIJ and SIK. Ish. Either this is just not vague, but too many symbols, This seems like too many symbols, and we have to translate all of these symbols into the visual representation, which we can understand, and that is kind of, yeah, a lot of work. We have the ith activity, and we have the jth activity randomly selected, and we have the set age Sij. This and this is the set Sij. Cool. And we are saying we have selected a random activity K, let's say K. And okay, now Sik would be defined by all the activities in this range and all the activities which end here. So should basically the whole thing. Okay, and then AIK is the set of activities which are exclusive, which are mutually exclusive, and Aij is the set of activities which are mutually exclusive in the set Sij. Sij is this set, and Aij, Aij is the set of largest set of mutually exclusive activities in Sij, and Sik is another thing, and Aik is the best subset of mutually exclusive activities in this set from this set. And that is just too many words. That finishes before AK starts, so that AIK contains. Okay, what does AIK contains? AIK contains activities in this set and in this set. So that AIK contains the activities in AIJ that finish before AK starts, and AKJ contains the activities in range Aij that finish before AK starts. That finish before AK starts. SIK. Okay, thus we have Aij equals AIK union AK union AKJ. Okay, this seems to be crazy, making the greedy choice. Okay, let's skip over this because this thing is not making a lot of sense. Yeah, this thing is not making a lot of sense. I mean, I'm not saying this is senseless, but it is just I'm unable to understand this. Making the greedy choice. Okay, what if you could choose an activity to add to an optimal solution without having to first solve all other subproblems? That could save you from having to consider all the choices inherent in recursion. 15.2. Okay. In fact, for the activity selection problem, you need to consider only one choice, greedy choice, when we have a bunch of choices. Hello, bro. Which handbook you told me about? CP, I forgot the name. Yes, that is the exact name. CP handbook. Yep, there you go. CP handbook by Mr. Anti Laxon. And okay, so we just have to consider one choice out of all the available choices in a DP solution. That choice is greedy. What is the greedy choice for the activity selection problem? Intuition suggests that you should choose an activity that leaves the resource available for as many other activities as possible. Of the activities you end up choosing, one of them must be the first one to finish. Of the activities you end up choosing, one of them must be the first one to finish. Makes sense. Makes sense. Intuition says, therefore, choosing the activity in S with the earliest finish time, since that leaves the resource available for as many activities that follow it is as possible. Yes, that is true. If more than one activity in S has the earliest finish time, then choose any such activity because they leave the same amount of time remaining for other activities to take place. Okay. In other words, since the activities are sorted in monotonically increasing order by the finish time, the greedy choice is activity 1. Choosing the first activity to finish is not the only way to think of making a greedy choice for this problem. Exercise 15.13 asks you to explore other possibilities. Okay, let's say we are making the greedy choice based on when our activity finishes. And if that is the case, and if yes, that is the case, then how, if that is the, if that is the case, then how do we like prove that this is the correct one? Once you make the greedy choice, you have only one remaining subproblem to solve. Find activities that start after AI finishes. Yes. Why don't you have to consider the activities that finish before AI starts? Because if SI is smaller than finish, and because FI is the earliest finish time in any activity, no activity can have a finish time less than or equal to SI. Makes sense because yes, that is the smallest. Thus, all activities that are compatible with activity AI must come after AI finishes, must start after AI finishes. Okay. Furthermore, we have already established that the activity selection problem exhibits optimal substructure. Let SK be the activities that we choose, or the set of activities that start after AK finishes. The set of activities that start after AK, a given activity finishes. If you make the greedy choice of activity AI, then SI remains as the only subproblem to solve. As the only subproblem to solve. Okay. You gave nope, I did not give yesterday's context. I saw the first question, which was yes, all the sides must be equal. So x1 is 10 and x2 has three numbers 1, 2, 3. Numbers 1, 2, and 3, then absolute difference is 24, like this. X1 is 10 and x2 has first three numbers 1, 2, 3, then absolute difference. Okay, you are saying okay, in one set we just have 10 three times, and in the other set we have three numbers 1, 2, and 3. Then the absolute difference is this. Yes, so this is what we are calculating, right? In that, okay, shit. Here, x1, both of them have to be vectors, right? In the problem, both of them had to be vectors. So they would be like 1, 2, and 3. And in the second vector, if you go with this example, the second vector would have 10, 10, and 10. And the answer would be, when you are fixing this 10, then you would have 3 into 10, like, right? 3 into 10 minus the sum of this whole thing. You see where does this element occur in this thing, right? And like, yeah, you will end up here where onto the right everything is bigger than this number, and onto the left everything is smaller. And you also have a prefix for this, prefix sum 1, 3, and 6. So you take the prefix value here, multiply your chosen number with how many numbers are onto the left. There are 3. So 3 into 10 minus the prefix of the last sum, which is 6. Right. So this turns out to be 24. Now you go with this number. And since they are the same number, this will also turn out to be 24. And now you go with this number, which is also 24. And the final answer would be 24, this number plus this number plus this number. 24 plus 24 plus 24, 72 would be the final answer. No, I'm talking about a particular calculation like I told you that we do x into the number of elements before minus x into prefix sum, and for numbers higher it will be prefix sum minus x into number of elements after x. Yes, yes, that is correct. That is correct. When you have made your choice, then you will just do, yeah, that. Your chosen number into the count, which are smaller, multiply this thing minus prefix smaller, this is like on the left part, plus prefix bigger, minus count of numbers that are bigger, CB into X. And yes, amazing handwriting. Yes, that would be the thing when you have fixed one of the numbers. So that is nice. Yes, this is the thing, right? Furthermore, we have already established that activity selection provides optimal substructure. Okay. One big question remains. Is this intuition correct? Is the greedy choice in which you choose the first activity to finish always part of some optimal solution? The following theorem shows that it is. Yes. Is the intuition correct? Right. It is easy to get intuition about greedy algorithms, but how to prove them that they are correct? Consider any non-empty subproblem K and let AM be an activity non-empty subproblem SK, where SK is the set of activities which end after, which start after AK finishes, like to the right, and let AM be an activity in SK with the earliest finish time. Then AM is included in some maximum size subset of mutually compatible activities of SK. Okay, why is that? So they are saying this thing. They are saying we have our number line and we had our activity AK, which began somewhere and ended somewhere, and now we have SK. SK is the set of all the activities which start after AK finishes, like which are mutually exclusive to the right of AK. SK is this set. And now they are saying AM is one activity in this set, which is, let's say here, AM. And AM has the earliest finish time. That is, all the other activities which are in this SK set finish later, finish after AM finishes. And they are saying whatever our final largest set of mutually exclusive activities in SK is going to be one of those largest subset is going to contain AM. That is the theorem. And now the proof. Let AK be the maximum size subset of mutually compatible activities in SK. Okay, okay, we can go with that. And let EJ be the activity. EJ be the activity in AK with the earliest finish time. Okay, so now we have in this SK set, we have taken a subset of some activities. We are calling it AK, right? We are calling it AK. And AK is a set of mutually exclusive activities in SK. Makes sense. Mutually exclusive, that is, they do not have overlapping times. And among these mutually exclusive activities, we are saying this AM is the one with the earliest finish time. Okay. If AJ equals AM, we are done since we have shown that yes, and AM is our choice. Since we have shown that AM belongs to some maximum size subset of mutually compatible activities. If AJ is not equal to AM, if AJ is not equal to AM, AJ is the activity which has the earliest finish time in the AK set, and AM is the activity which has the earliest finish time in the SK set. And in AK, all the activities are mutually exclusive. In SK, they are overlapping or could be overlapping, does not matter. If AJ equals AM, we are done, right? Because AK is something that we have to get on to, right? And AM is our choice. And if AM is AJ, then we are good to go. But if it is not, AJ is not equal to AM, then let the set A dash K be the original AK set, and we have removed AJ and put forward AM. B shit. Shit, this makes sense. B AK, but substituting AM for AJ. Okay. The activities in A dash K are compatible. That is, they do not overlap. Makes sense. Which follows because the activities in AK are compatible with AJ, and we just removed AJ and we added AK, and we removed AJ, this jth activity from the optimal subset. We removed that and we have put in AM, and AM is going to be compatible with the rest of the activities because AG was compatible and AM finishes before AJ did. In AK to finish, yes, the finish time of M is smaller than or equal to all of the other finish times. Since AK dash equals AK dash size, we conclude that yes, the size also didn't change. So we conclude that A dash is the maximal subset of mutually compatible activities, and that is true. That is like makes so much sense. Sure. Yeah, although you might be able to solve the activity subproblem with dynamic programming, theorem 15.1 says that you don't need to instance. Instead, you can repeatedly choose the activity that finishes first, keep only the activities compatible with this activity and repeat until no activities remain. Moreover, because you always choose the activity with the earliest finish time, the finish times of activities that you choose must strictly increase. You consider each activity just once overall in monotonically increasing order to finish times. We just sort the activities based on their finish times, and we choose the one which is right here, and we'll have a pointer, and our pointer will always point to the first activity which is choosable. And when we do make a choice, we will move our pointer to the right till we will keep moving our pointer to the right till the current activity becomes choosable based on the last choice that we made. Okay. An algorithm to solve the activity selection problem does not need to work bottom up. Like a table-based dynamic programming algorithm, instead it can work top-down, choosing an activity to put into the optimal solution that it constructs and then solves the subproblem of choosing activity from where. An algorithm to solve the activity subproblem, the activity selection problem, does not need to work bottom up. A recursive greedy algorithm, okay. Bottom up would be when we are making our choices. You got mad consistency. Twitter account, shit, X account, just my name, shit, yes, my name 137 makes sense. And what is happening in Waymo? Shit, I've heard Waymo is something, but yes, I don't use Twitter that much. Shit, I don't know who they are. And yes, the consistency does get on, like it gets difficult, but okay. An algorithm to solve the activity sub problem does not need to work bottom up. That means bottom up, we have initially zero activities and we are incrementally making our solution from ground up, bottom up. Okay. And like, yes, bottom up means we are first solving sub problems, smaller sub problems. And whenever we go to a bigger sub problem, the smaller sub problems on which this bigger one depends on, they are already solved. So that is bottom up. Instead, it can work top down. Instead, it can work top down when we are making a choice and the subproblem on which the choice depends on, they are not yet solved. So we call the original function recursively on those subproblems to solve the subproblems and choose the one which is the best. That is top down. Okay. Choosing an activity to put into the optimal solution that it constructs. Choosing the activity to put into the optimal solution that it constructs, and then solving the subproblems of choosing activities from those that are compatible with those already chosen. So subproblems for subproblems, plots within plots. Yes, dune greedy algorithms typically have top-down design. Okay, make a choice and then solve a subproblem rather than bottom-up technique of solving subproblem before making a choice, because I think the order does not matter because every subproblem only depends on the best greedy subproblem. So yes, because we do not have to solve all of the subproblems, we would just be solving the greedy one, and thus we are saving ourselves some compute time. So that is nice. A recursive greedy algorithm. Now that you know, you can bypass the dynamic programming. And it's okay. I would like to like point out one more difference. A node on closed for, okay, that is something. Now, so this is yes, I would like to make one more distinction here for dynamic programming using iteration, dynamic programming using iteration in like bottom up approach. Here, the problem is, or maybe the problem or the requirement is that we solve all of the subproblems. We solve all of the subproblems. That is the thing. And when we are using iteration with bottom-up approach, with like tabulation to store data, and we solve all of the subproblems. But the thing with recursion, where top-down approach using memoization, memoization memorization is that we only solve the problems which need solving. So here we are not solving all of the subproblems. And in general, when we are doing a dynamic programming question, we often go with iteration. We often go with iteration because, first of all, with iteration, even though we have to solve all of the subproblems, the overhead to get to solve a subproblem is easy because you are just iterating through a loop. But here, to get answer to a subproblem, you have to call a whole different function, which is kind of high overhead. And generally, the number of subproblems, the total number of subproblems is equal to the number of subproblems which are required to solve the question. And yes, so the number of subproblems we solve in recursion Let's say it is x. It is also x generally speaking in iteration. So we go with the iteration approach. But in some cases, out of all the sets of subproblems, let's say x is the set of all the possible subproblems. If we use recursion, then we are only solving a smaller subset of these subproblems. And that is very good because there are a lot of subproblems which we are not solving. So that is kind of nice. But if we were to go with an iterative approach, we would be solving all of these subproblems, which we don't need to be solving. So that is nice. And in greedy algorithm, we use recursion, it seems, because we don't have to solve all of the subproblems. We only have to solve the subproblems in which we are making the greedy choice. So yes, and yeah, since we don't have to solve all of the subproblems. We only want to solve the greedy ones. So that is nice. Hello, you said something. So that is why we use recursion with top-down approach in greedy algorithm, it seems. Now that you know, you can bypass the dynamic programming approach and instead use a top-down greedy algorithm. Let's see a straightforward recursive procedure to solve the activity selection problem. The procedure recursive activity selector on the following page takes the start and finish times of the activities, right? Represented by arrays S and F square, S and F, the index K that defines the subproblem SK to solve, subproblem SK to solve. That is all the subproblems which all the SK is the set of all the activities which start after SK finishes, after the kth activity finishes, and n the size of the original problem. It returns a maximum size set of mutually compatible activities in SK. The procedure assumes that the n input activities are already ordered by monotonically increasing the finish time. Uh-huh. And they are like, yes, in ascending order of the finish time. If not, you can first sort them in log n time and breaking ties arbitrarily in order to start and fictitious activities A0 and F0 where time starts 0. So that's the problem. 0, 0 is entire set of set activities S makes sense. We can add a dummy activity so that this thing works in a general case and we don't have to think about edge cases. It seems like your username is disabled. No. Hello. Everything is amazing. How are you? How is my username disabled? It is not disabled. There we go. Working just fine. Look at this. Nice graph. Here we have. This is pretty cool. And statistics. Yep. And yeah, everything is going on amazingly. Recursive activity selector. Yep. That is nice. And yes, this fact that our algorithm, we can add some buffer input data so that our algorithm works correctly and we don't have to look for edge cases is pretty nice. That is a pretty nice idea. I would actually like to take a screenshot because this is pretty cool. And this is how this thing works. M is the first choosable activity, while the starting time is smaller than finish time. Is smaller than the finish time of K. Keep increasing M, and also M is within the range. And now, if M is still within the range, then return AM. AM in union with, yeah, call the function again recursively or return an empty set if M went out of the scope. Makes sense. There is a like underscore in between. My bad. And there is still and there is very little standard approach. I've seen same reason for starting competitive program to prove myself. Flow. Yes, prove yourself. Yes, that is the thing, right? There is very little standard approach. Very little standard approach. This is very ad hoc, and the ways for learning. And yes, competitive programming is also very good because you are not just learning new things, you are also learning how to learn new things. So, like meta level learning, which is going to help you everywhere, not just in competitive programming. And I would say competitive programming is one of the hardest thing that someone can do in college, except if they are starting their own company, that would be harder. Startup. Okay. Figure 15.2 is somewhere. Shit. That looks like a CPU scheduling diagram. Okay, this is our buffer activity, A0. This is our buffer activity. This is what we choose. And then when we call the function, it returns AI activity. Now we are looking for activities which start after AI, which is A4. A4 is the first activity, which starts. A4 is the first activity which starts after AI ends. Right? Then we go with AI and we look for the activity which starts after A4 ends, which is A8. Then we go with A8 and we then choose A11, and this would be our final set. That is nice. And there is also this non-recursive approach. That is nice. Figure 15.2 shows the algorithm operates on activities in figure 15.1. In our given recursive call, this thing, the while loop of line 2s and line 2 and 3 looks for the first ST activity to finish, which is equivalent to this arrow moving from left to right here on each step, here, like that. And until it finds the activity AM that is compatible with the activity which we have already chosen, which is AK, which means that SM greater than equal to FK. Starting time of the mth activity which we are choosing after choosing K is after or at the same time that K activity finishes. If the loop terminates because it finds an activity, then we add it, take its union, and call the function again. And if the loop ends because we ran out of activity, we will return a empty set. The iterative greedy approach. Let's write algorithm for this. Hello, good morning. How is everything going on? Good morning at 1 o'clock. Is your Discord name Wallace? Yes, yes, that is. And stalking. Stalking is very common in code forces. We stalk everyone on code forces. We can stalk Mr. Tourist, which is nice. Look at him. And where is Dominator 69? He is now a GM, LGM, like very nice. LGM, bro is an LGM, and bro is at his peak form achieved. And shit, he has been going up, which is like pretty cool. And let's write a code for this. Attach target CP and activity.cpp and shit boilerplate and we'll just write a simple function main which will call a function and that function will return an integer solve. It takes in vector in reference a include vector and using namespace std right. And here, uh, we are writing an iterative approach here. And I is 0, I less than n, I plus plus, what is n? N is the size of a in n equals a dot size. And here, then, right, and we will say, we will also have the last time, L equals 0, right? And if AI and AI is sorted in, let's not call it AI, let's call it finished. And what we will do, since we don't know the caller of the function has sorted this thing or not, we will sort this thing on our own. Finish dot this thing and finish dot end. Cool after finishing, and if finish I is greater than or equal to the last time that an activity, shit, we also need their starting times. Shit, yes, okay, my bad. We also need their starting times. Reference start, right? The starting time of the ith activity is greater than or equal to the finish time of the last activity. Then yes, we are doing one more activity in rest initial equals 0, 5, return rest at the end. If this is the case, then we will go with AI, SI, and get, since we are sorting this, we also need to sort start accordingly with F with the finish. So it would be better to make a pair and then sort the pair depending on the finished activities, depending on their finish time. Vector times size is n, and here we can even do this. We can say this, and we, yep, after n we don't finish this. What we will do is for int I equals 0, and yes, this is kind of not exactly useless, but this is something. Times I dot first is the finish time, finish I, and times I dot second is the start time for the ith activity. Then we will sort the thing. Sort times dot begin and times dot end, and we can just call this sort function because when C++ compares two pairs, it first compares the first element and then the second element, and we only want our activities to be sorted according to the first element, which is the finish time. So that is nice, very nice. And times I dot second, which is the start time. If the start time of the ith activity is greater than equal to the finish time of the last activity, then rest plus plus and L equals times I dot first, which is the finish time of this current activity. And that is pretty nice. Let's create a vector, two vectors actually, start and finish. And we will copy the question from here, like the exact question. Stock, one of your students, Jiangli, not student, damn, his graph looks insane. Graph, this, um, yesterday I did division 4 and was able to solve only first two, but the first one was very simple. The first question was simple, but I was with a friend and my friend, so we, the question was, we have four sticks A, B, C, D, and we have to say yes or no if we can arrange these sticks in a way so that we can make a square. So My immediate response was if A equals B equals C equals D, then we can arrange them in this manner and we have a square. But one of my friends, like, yes, I was only talking to one friend. He said that, let's say, there was an example actually, which was 1, 1, 1, and 5. And he said we can make a square with these lengths. Let's say we arrange the 5 ones like this and the sticks with size 1 like this. We have a we have a square. We have a goddamn square right here. Shit, but I didn't consider this thing. And this is crazy. This is crazy. We can skip the smallest, simplest things. This is crazy. This was pretty nice actually. But the answer for this one is no, because in the question it is specified that we should not have something like this lying around. So that is nice. That is nice. It would be a rectangle. This thing is a square. If we have placed, well, this side is equal to this side, and if we place these two sticks at a distance of 1, then this thing is a square, and that is crazy. That is crazy. If we have like three sticks with length 9, 9, and 9, and one stick with length 10, right? We will have one unit length lying around there, but here we have a square. We have a square of size 9, which is crazy, right? This is also 9, and this we have one like lying around here outside. That is also pretty cool. The definition of a square is all sides are of equal length. Yep, we just have one thing outside which we are not considering as part of the side. But yeah, the answer for this is no. The answer for this is no. But it's still the fascinating part that I'm trying to point out is that this concept of making a square didn't even occur in my head. So that was nice. What you are saying, it seems like after solving complicated problems, human brain struggles to solve simple problems. Yes, because I would say the approach, the mindset with which I approached the problem was that this is very simple and I do not have to think too much about this problem and just check if A equals B equals C equals D. Yeah, so that limited my thinking capacity, I guess. I was saving compute time. Okay, this is the start times 130. Tunnel vision. Yes, tunnel vision. Yes, happens in chess all the time. Checkmate on the board. We are just going somewhere else. Problem G is a good problem. Okay, let's look at problem G. Wait, this is going on. Why does it say enter? G, okay, yes. G, the last problem. Muhammad Ali. Should it is literally Muhammad Ali. Muhammad Ali has an integer array A1 to AN. He can change, replace any subset of positions, changing position I, cost Ci, and replaces. He can replace any subset of positions, any subset of positions, changing position I, costs Ci, and replaces AI with an integer of his choice. Okay, the positions that he does not change must retain their original values. After all changes, we can index this I, okay, a drop if the final value in the position I is strictly greater than the final value at position. Call an index a drop. Okay, if the current value, if the ith value is smaller, is greater than the next value. Since there is a drop in the value, okay, Muhammad Ali wants the final array to contain no drops. So either they are equal Either the values are equal or they are in ascending order, monotonously increasing. Okay, non-decreasing. We have to make the whole thing non-decreasing. Find the minimum cost of changing required to ensure that there are no drops in the array. Seems like dynamic programming. E and N, the cost. Okay, for this, answer would be 0. This second one, yeah, answer is 0. For this, however, answer would be 3. We can make change these numbers. Answer would be, wait, yes, 3. Or could there be a better way? Mm, this also depends. Okay, yes, the cost. Normally, if the cost was same, this would be the number of inversions, or shit, this would be true. If the costs were same, there was one thing you said in when we were talking about policy-based data structures, that we can get order of element and go from right to left and find order by key, and that would be, and we will keep accumulating or adding to a variable the order of key as we are going from right to left, and that would give us how many keys which have been added to our tree are smaller than this key that we are going to add. That would give us the total number of inversions. Okay. Anyways, that is not very related to this. Okay. Here, this is these two are already nice, so we should, but the cost here is 100, so no, we won't go with this. And this seems like dynamic programming. Cost. If I have the choice of changing this and making it compatible, yeah, changing this and then add this cost. If I do not change this thing in this, total number of possibilities will be 2 power n, but not all of them are correct. Here also the answer is 0. Yes. And here the answer will be 3. Yes, it is 3. Here 2 makes sense. Here 0. And here we don't want to change these two things. Fine. Uh, we can change this, just this to be equal to 2. So answer is 1. Answer is 1 here. And since we can change a given integer to be equal to any number, that is nice. We want the current number to be between the left and the right number. Okay. Since here this number is compatible with the left number, but not compatible with the right number. So either we change this or we change this. And we can change, yeah, we can change this or this. Well, this feels like dynamic programming, but exactly where, wait, shit, here, yeah, we have to change, we change this one or the other ones, or either we do change this or we don't change this. That is a choice. Let's go with this methodically or something. At every number, we have a choice to change it or not. If we do change this, the cost would be the best thing here, but also to which value. This also depends to which value are we going to change this to. The best answer when we only have one element is 0. The best cost is 0. And when we add this element also into our vector of like things that we are considering, then since we see that this one is not compatible with this one on the left, right? This is not compatible with this one on the left. So either we change the one on the left or we change this one. We can change this one and that would have no effect of on what we have done on the left, and we can go with the best cost and add the current cost. But if we do change this one, that would have dramatic effect on what we do on the left. So that would mean that we should go from the right, because the effect affects things on the left. We want the things on the left to be smaller. So here, these two are compatible. So best choice till now is 0, right? Yeah, best choice is not changing any of them. And here also compatible. These three elements are compatible with each other. So that is nice. Now, this one is also compatible, which is very nice. So cost for the 4 later elements is 0. But if we add this one, this is not compatible. So either, but shit, this will also have a trickling effect. If, yeah, this would also, because this value could be higher than the highest value here, in which case all of them would have to be increased if we don't increase this. Yes. So yeah, shit. The number of subproblems is too much in this, it seems like. Hello, I'm new here. What problem is this? And in which language you're coding? Bro, this is this problem and we code in C++. C++ is nice. Let's have a stopwatch for this. Okay, we are now officially doing this one. And I'll put this right. Okay. 10, 9, 8, 7, 6, 5. This is all wrong. Shit, if I do make this change, then how many numbers on the left are all the numbers on the left have to be smaller than this, and all the numbers on the right have to be greater than or equal to this, right? Yes, that is one thing. And okay, okay, what would be the cost if I shit that would require n square time, and we can go for n square time. We can ask that if I do not change this number, or if I do change this number, If I do change this number, then the cost would be changing this number, right? Changing this number. And if I do not change this number, then all the numbers to the left would have to be smaller than this. And that would be one cost. And all the numbers on the right would have to be greater than this. And if I do that, then the cost would be the sum of these numbers, which are on the right and greater than this current number. And the best choice for the numbers that we are changing would be for them to become equal to this number, right? Yes. On the left for all the numbers, let's say this, for all the numbers that are bigger than our current number. Well, I think we don't have to look in both the directions simultaneously. We can look in just one direction. If this is compatible, if we are here, we can go through the left. If we change this, if these are like not compatible, then either we change this and that would be our cost. If we do not change this, then all the numbers on the left which are bigger than this must become smaller or like equal to this, and that would be the cost. And we will take that. Okay, shit, yes, this is doable, this is doable, this is, we can do this. Okay, shit, what is this? CPP, C++, int n, take in n, okay, vector in a size n for int reference x in a, c in x, and stop the LSP stop, shit, LSP stop. Now LSP is stopped, and long, there are two things, pause is also there, and a change this with pause and long response equals initially 0 for n I equals 0, I less than n, I plus plus, and on to the left. If, okay, first one is like always compatible, so we will start from 1. If we see that AI current value is smaller than AI minus 1, then we have to do something. Yep. If the current value is smaller than the last one, then we have to do something. Long previous. If we change all the previous values, right, for which for int I equals, for int j equals 0, and j is smaller than I, all the values to the left of I, j plus plus. If aj is greater than ai, if aj is greater than ai, then pref plus equals cost of j, changing j. And we will not be adding, will we ever be adding the same cost multiple times? Yes, we don't want to add the same cost multiple times. We will have a vector, but yeah, we might be adding the same cost multiple times, for which to avoid that, we can have a Boolean vector change size n, and initially everything is false. Have we changed the current value? And if not, then this. Okay. If that value is bigger, right? And if changed j, if we have already changed j, then we will just change the value and we will say a, or shit, we don't even have to change the state. We'll just say if AJ is bigger and not change J. If J has not been changed, then we will add the cost to previous and change J equals so J has been changed. Right, that would be the previous cost. And if previous is smaller, this might fail if previous is smaller than or equal to this thing. If at the same cost we are able to change multiple things, then we would prefer changing multiple things instead of changing just one thing us at a cost. I would say. Yes. Okay. I think that is the right thing. Okay. Hi. Hello. I am fine. How are you? And if previous less than or equal to the cost, current cost, AI, then we will change the previous things. And yes, we will say res plus equals previous shit. Okay, shit. We have changed a lot of things. We have changed this thing. Shit, we have made a lot of things here true. But if we do not go with changing the previous values, then we have to fix them and make the things that we made equal to true false in this loop, for which we would need a queue. And whenever we are making a new thing equal to true, we will go through the queue if we are not changing the previous values and make all of them equal to false again, because that is how the state was earlier. Shit, and that just seems like too much work, and that seems like it is wrong. And now is the time to, I guess, come back the main topic. But this question is nice. Thank you for asking. Which question are you solving? Was trying to solve? Yes, trying. Trying is, yeah, trying this question. Division 4, last question. G. So, shit, it is like already here. And now getting back to this. Yes, what we were doing is this. Um, we can make this full screen and shit, that is too much information. Slash, come on, shit, what was the name? Activity, activity.cpp. Yes, and in our main, the start times are 1, 3, 0, 5, 3, 5, 6, 7, 8, 2, 2. That is nice. And with the end times, or we call it finish times are, yes, finish 9, 9, 10, 11, 12, 14, 16. That is nice. We everything is going everywhere else. That is great. One of my friends solved G yesterday. That is cool. Please recommend book or playlist to reach 1400. Yep. CPHB, Competitive Programmers Handbook. This thing you can, okay, the things in this book are not explained comprehensively, but you can use this book at least as an index so that you know which topics there are. And if the material, if the explanation in this book is not enough, then you can go on to YouTube or go on to CLRS book to get a more detailed explanation of some topic. So yeah, this book is pretty cool. You can use this book. That would be nice. And let's call the function. Check the whole signature. Okay. Solve or answer is um, solve, finish, and start. And also we have to include compile. It took 1.1 second to compile, and the answer is 4, which is the correct answer. So that is nice. That is nice. Okay, went through the theorem. We have we went through this diagram, and yep, that is the recursive thing. And let's, instead of outputting our integer, we will return a set of integers, which is the correct answer. Like, which activities have we chosen? That would be our answer. Set of integers, integers does not make sense. We will return a set of pairs. And should, okay, and we will also use some crazy operator overloading to print a pair onto the screen. Pair of integers, and we will call it res. And not res plus plus, but res dot insert times I, and return res at the end. And yeah, see out. Answer is line for auto s in shed set of pairs of integers. Res equal solve. We also have to change the function signature above finish, and start file set of pair in P, and I think we have to include set. I don't know. Set might be something. Okay. Now here in let's see out S. And this is going to work. Let me show you how. Return output stream or reference to output stream and operator. This when the first argument is a output stream reference, we will call it OS, and the second thing is a pair of integers, reference P. And I need some LSP support here. And so LSP start lang D. Okay, something is wrong. Host string, include host string. A type specification required host string reference. Okay, I think I can turn off the LSP. Okay, cool. Yeah, when this thing is required, when this thing is given, cout or not cout, OST takes first uh, closing bracket, then p dot first, then a comma, then p dot second, then a closing bracket. That is nice. And we will even say a closing bracket and a new line and return this whole thing. No error. That is nice. So these were the things which were the chosen one, the activities which were chosen. And shit, we should like print them in the opposite order because here we have taken finish at the first value and starting time as the second value. So here we should say s dot second comma s dot first. Okay. Yes, they C++ doesn't know what to do with this pair of integers. Make this a pair of integers. Hey, shit, that is even worse. Yes, that is worse. Uh, okay, shit. Output string cout making operands. Shit. Okay, okay, okay. I think I messed up here. Yeah, that was the thing. Cool. Why was there this error? Because when we are saying that p has to be a reference, if p is like make do value, which we just create at this point and which is not related to anything, then this will give us error. But this would work like if we compile this right now, error. But I think if we make this a R value reference, this should work now. This does work now. So that is nice. So yeah, that was it. Just started studying programming in college. What is tips you would give me? I would just say just don't stop and get your hands into whatever you can in programming sense. uh, just get your hands dirty and s- just keep doing new things. And yes, that is the thing. That is what you can do. And yes, also don't be afraid of new things. And yeah, don't be afraid of learning new things. Just keep learning new things. That is the best thing. And be curious. Be curious. Okay, so we have done this one. Yep. The procedure works as follows. We know how the procedure works, but anyways, the variable key indices indexes the most recent addition to A corresponding to the activity AK in the recursive version. Since the procedure considers the activities in order of monotonically increasing finish time Fk is always the maximum finish time in any activity A. Yes, 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 yes. The last one, Fk. Lines 1 to 2, select 1, 2, 2. This one, 1, 2, 2. The initial thing, and set k equals 1, which is the last activity that you chose. Initialize A to contain just this activity and initialize K to index this activity. The for loop in these lines finds the earliest activity as K to finish activity in SK. To finish, the loop considers each activity em in turn and adds em to a if it is compatible with all previously selected activities. Such an activity is the earliest in SK to finish. To see whether, yeah, this just like going normal loop and finding the first activity which starts after the currently chosen activity finishes. And on to exercise. Yes. Given Give a dynamic programming algorithm for the activity selection problem based on recurrence. Have have your algorithm compute the size Cij as defined above and also produce the maximum size subset of mutably computable activities. Assume that the inputs have been sorted in equation and compare the output with the greedy algorithm. Compare the running time. Okay, shit that no, I won't be doing that. I won't be writing a dynamic programming solution to this one. Dynamic programming solution. I would say the dynamic programming solution in this one would be very similar to the question that we were just doing from yesterday's contest. Mm, yeah. Suppose that, and yes, why not? Because I think that why not do that to this question right now? Because there, because you don't have to take up every burden, I think. Yes, you don't have to take up every burden, I would say. Suppose, and here the main thing is greedy. So yeah, no dynamic programming here. Suppose that instead of always selecting the first activity to finish, you instead selected the last activity to start, the last activity to start that is compatible with all the previously selected activities. The last activity to start which is compatible with, okay, how this approach is describe this in greedy, describe how this greedy, how describe how this approach is a greedy algorithm and prove that it yields an optimal solution. Okay, if instead of choosing the activity which finishes first in our number line, we have a bunch of activities, some of them compatible, some of them are incompatible with each other, like this. And initially we our set is empty, we haven't chosen any activity, and then we are choosing the activity which starts the latest start starts the last. So we have to say why this is greedy and then that this produces the optimal solution. So if we work this out, first of all we will choose this activity, its starting time is the last, makes sense. So yeah, this one, activity number one we will call it. This is 2, 3, 4, 5, this one is 6, right? And now among all the activities which we can choose, this one 2 is the one which starts the latest, that last, and now we have chosen 1 and 2, and now 3 is the one which starts last, 3, and we cannot choose 4 with chosen 3, so we go with 5. 5 is the one which starts the last. This is our answer. And first of all, why is this greedy? This is greedy because the way that we are making our choice only depends on what is the best local choice right now. Hello, how is everything going? Yeah, this is greedy because whenever we are making a choice, the choice only concerns itself what is the best choice right now. Yes, so that is nice. And then, so yes, that is why this algorithm is greedy. But why would this give us an optimal solution? I would suppose that whenever we are choosing one activity, let's say we have chosen one activity, right? And we have the set of all the other activities which could be chosen next. Let's say we have chosen the activity according to our greedy algorithm, this second one, which let's call this A, G, and this set of activities from which we can choose, let's call this set S. And let's say the actual answer is SB, as in S best, right? And we have chosen AG. So if AG is in SB, that is nice. We want to convert this S set into SB, and our choice AG from S is one of the choices in SB. So that is nice. But if AG is not in SB, then the activity in SB which finishes the last, or yeah, which starts the last, we can remove that activity and put AG here, because AG is already compatible with all the activities we have chosen, because AG is something from the S set. And yes, so using AG, it would be compatible with the activities which we have chosen right now. And AG would also be compatible with all the activities in the SB set, because all of those activities would be compatible with the one, let's say, mm, SBG is an activity, or ABG is one activity from this SB set which has its starting time the furthest apart, like the highest starting time. So we are saying that AG, which is the activity with the highest starting time from the all the possible activities, if this thing is not equal to this, then we can remove this SVG from the SV set and put in AG. So the size of this SB set has not changed, and also AG is working in SB. So that is nice. So if we do apply this greedy algorithm, we will have the best answer. So that is pretty cool. Now, not just any greedy approach, not just any greedy approach to the activity selection problem produces a maximum size set of mutually compatible activities. That's it. Then there are elements of greedy strategy. I guess shit. Reading on stream doesn't seem to be the best strategy. First of all, for myself also, because yes, when I read normally off the stream, I take a lot more time than I'm taking right now, and I don't have to speak so much when I'm studying on my own. But on stream, I have to speak. So that is a downside. And second of all, I don't think these streams are very helpful for the people also who are watching. Yeah, this is a gentle reminder to myself. Solving questions is much nicer on stream, right? And there are three questions left. Not just any greedy approach to the activity selection problem produces a maximum size set of mutually compatible activities. Give an example to show that the approach of selecting the activity of least duration from among those that are compatible with the previously selected activities does not work. And we can prove this by contradiction. They are saying if we write a greedy programming approach, in which we are always choosing the activity among all the possible choosable activities, we are choosing the one with the smallest duration. Well, if we are doing that, let's say this is our number line, and we have one activity with duration 1. Yes, and we have another activity with duration 1 here, and we have another activity with the duration like 5 here. So according to this greedy programming approach, we would choose, let's say, this activity, or let's say this activity has a size of 2, right? According to our greedy approach, we would choose this activity. Or wait, yes, sure. Let's resize or rearrange these. Say our activity with a duration of 1 is here. Activity with the duration of 2 is here, and activity with the duration of 5 is here. And if we choose activities based on their duration, the smallest one first, then if we choose this one, activity, this one, then we won't be able to choose any of them. But if we were to choose like the activity number 2 first, and then we could also have chosen 5, which is better, and that's nice. So yeah, this one doesn't work. You are given a set of activities to schedule among a large number of lecture halls where any activity can take place in any lecture hall. Shit, now we have multiple cores in our processor used to schedule all the activities using as few lecture halls as possible. Given an efficient greedy algorithm to determine which activities should use which lecture hall, this problem is also known as interval graph coloring problem. It is molded. Give an efficient greedy algorithm. Okay. Efficient greedy algorithm. We have to give a efficient greedy algorithm for this. Okay. When we have multiple cores, yes, that is the thing. This is called interval graph coloring problem. Consider a modification to the activity selection problem in which each activity AI has, in addition to a start and finish time, a value vi. The objective is no longer to maximize the number of activities scheduled, but instead to maximize the total value of the activities scheduled. That is the goal, to choose a set A of compatible activities with each other such that this give a polynomial time algorithm for this problem. Shit. Okay, these two problems are difficult. First is this one, when we have multiple lecture halls and we have to arrange lectures in those lecture halls which are compatible with each other using the minimum number of lecture halls. And here, right, that is what we have to do. You wish to schedule all activities using as few lecture halls as possible. And here, the problem is we have been given, in addition to the start and finish time, values to activities, and we have to choose activities which are mutually compatible with each other, and they give the maximum value possible. Okay, those two problems are crazy. Activities which are mutually compatible with each other and give us the maximum value. Like, have activities, and our main goal is can be solved using greedy algorithm. That is crazy. It's staring at a line. That is, yes. And interval graph coloring problem. Let's first focus on this one. Modification to the activity problem. We also have values with start and third time, starting and ending time. We have values. Among all the activities right now, given right now, which activity should we choose to maximize? Yeah, to maximize the thing. I think maybe density would not matter. Density would be like if each one of these has some values, density would be this length or this value divided by the length, this value divided by the length, this value divided by the length, and choosing the one with the maximum density is not pretty cool, right? Right. Choosing the one with the maximum density is not very cool because in one example, we might have some activity with a very big density. But if we were to go with that, we would not be able to choose two different activities whose density would be, say, yeah, if we, this one V2 would have the highest density. But if we were not to choose V2, we would have V2 is smaller than V1 plus V3. This is supposed to be V3. Yeah, so maximum density is not right. And choosing the one which finishes first is also not right. Polynomial time algorithm, we can go up to n square in this one, or n cube, does not matter. If we do make, let's say, if we do fix one thing and we say, this is our choice right now, then there would be a bunch of activities we could choose on the left and a bunch of activities we could choose on the right. Right. And that is our sub problem. Wait, shit. Uh, yes. And whatever activity we go with, we will get a value here. And this is just the same as the original problem now. There are activities on the left we could choose or activities on the right we could choose with this one. And we have to get the best value from the left and the best value from the right and the best value from the left, and we will add that to the value of this activity. Shit, yeah, we will just have to read some more before being able to solve this. Hello, China on top. How is China on top? That is crazy. And shit, yes. Uh, I would say, I guess I can end the stream now. It has just been 2 hours. Yeah, I think I can end the stream now. And from tomorrow on, I will be just doing questions here on the stream, which is much better than trying to read something and learning problem set. Yeah, we'll be doing questions. 1500. Yep. And yeah, that is nice. Okay, I will not end the stream. I'm not ending the stream. Yes, we'll give virtual contest for this one. Wait, system testing is going on. We cannot give virtual contests. So we will just solve these questions normally. Yeah, this tree, and maybe even hopefully this one. Let's see how it goes. Square, that is simple. I read the problem yesterday, so that is nice. I can do this. Boilerplate in yeah, A, comma B, comma C, comma D, taking A, B, C, D, and if A equals B equals and 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 B equals C and C equals D. Yeah, if that is true, then all of them are equal to each other. And then C out, yes, with the ending line, else C out, no. We can submit directly, and probably this one is correct, right? Contest is over. Okay, that is fine. Should we cannot submit it. Shit, we cannot submit somehow. Submit. Contest is over. It is over, but we are up solving. I guess. Shit, we cannot submit. We cannot submit right now. That is the reason. Anyways, let's. Yeah, we can submit later. Then we will just solve them. Kavira is writing is okay. Shit, I also read this statement yesterday. Kawa has is writing his girlfriend's name. He has n cubes each, n cubes each with one lowercase Latin letter written on it. They are arranged in a row, forming a string. S. His girlfriend's name is also a string T consisting of n lowercase letters. To prove his love, he must check whether it is possible to rearrange the letters of the string S so that it becomes her name T. Yes, one of them is S and one of them is T. All we have to do is can we rearrange one to make the other one? We can just sort and see if they are equal to each other. And then take an N and shit string S and T, take an S and T, sort S dot begin, S dot N, and S, replace with T, yeah, C out, depending on S equals T, question mark, yes or no, and a new line. That is the solution. Just believe me. Well, we cannot right now. Yeah, it does say correct answer. We cannot submit somehow. Isa Martin has n toys arranged in a row. The ith toy has an integer AI. Has an integer AI. He wants to sort them because otherwise his mother would scold him. However, Isa Martin never liked arranging toys in order, so his friend Jahon gave him a magic wand. Well, unfortunately, Jahon made a small mistake while creating the wand, but couldn't wait any longer and decided to use the broken wand anyway. The wand can swap two toys if their integers are have different parity. That is, one is odd, other is even. In other words, you can swap toys in positions I and J if they have different parity, where more is the remainder of integer. Now he wants to know the lexicographically smallest arrangement he can achieve using his broken wand. Using his broken wand. Okay. Yes, we can do this. Yes. Here, the answer would be 1, 2, 3, 4. 1, 2, 3, 4. Here, the answer is this number itself. Here, the answer is 25317. We, with 2 is even. Yeah. So, answer would be 1, 2, 3, 5, 7. 1, 2, 3, 5, 7. Yeah. Here, answer would be this number itself. Yeah. Because we cannot change anything. Like, makes sense. And n, taken n, and okay, we have taken an n vector in A and n, right? And we even equals false and odd equals false. If we have at least one even and at least one odd number, then we are good to go. And we won't even have, yeah, we do need the order later on, right? So for int I equals 0, I less than n, I less than n, I plus plus C in AI. And if AI is odd, then odd equals true. We have seen an odd number, and else even equals true. We have seen an odd number and an even number. That is pretty nice. And now if odd and even, if we have seen odd and even, then we can just do sort a dot begin and a dot n, and for in I equals 0 or in x in a, or for in I equals 0, I less than n, I plus plus C out AI after sorting AI and a space or a new line depending on I equals n minus 1. Okay, cool. That should be the answer. That is the answer. But we cannot submit, so yeah, we don't know. That might be wrong. Yet another array problem. You are given an integer n and an integer e of length n and an array e of length n. Find the smallest integer x, an integer n and an array of length a. Okay. Such that there exists an index where GCD equals 1. If no such, there exists an index with GCD AI x equals 1. If no such x exists within the range, this output minus smallest integer. Should we cannot choose one, which is pretty nice. We cannot choose one. 2 would be the first choice, and there are 10 to the power 5 elements. 2, 3 with anything. We want the GCD to be, so we can just take the smallest number. We and shit, AI can also be very big. Okay, AI can be very big. We will take the smallest number in the whole thing, not always the smallest number, it won't always work. The GCD should be 1 when we have chosen the number. Here, this is the question. We just want to return a number, the smallest number, and if we were to take GCD with that number, then you won't have it. Okay. Okay. We don't want to brute force. Should Can we take GCD of all the numbers? Yes. Get the GCD of all the numbers. So all the numbers would be divisible by that number, and yes, just take the GCD of all the numbers. GCD for this number would be 3, but would be 3. GCD would be 3, right? So all the numbers are divisible by that number. Mhm. And GCD plus 1 would be one answer. That is not always the answer, is it? Here, GCD is not 4. Here, GCD would be for this and this. The GCD is 24, literally, this number. But the factors of this number would be 2 into 3, 6. 6 into 7, 0. 6, 12. 12. Yeah, and this is divisible by 12. So 12 would be the GCD, but the actual answer is 5. Okay, we want the GCD, the smallest number with which the GCD is with which the GCD is 1. Hmm. Okay, for a number to be not a GCD, since our range is 2. If we are saying that 2, since our range goes from 2 till 10 power 18, right? And we are saying that 2, if 2 is not GCD, I think we can brute force it. If 2 is, what is the minimum possible answer in this range from 2 to 18 for a number that would be factorial? How big is 18? Not factorial, uh, x factorial. For x to be not an answer, all the numbers in this thing should be divisible by numbers from 1 to x. Right, we'll see. We can write a little program. Fact.cpp, and main and I equals long f equals 1, and for in I equals 0, I less than n, and I plus plus. What is n? N is nothing. While f is smaller than range is equal to The maximum value that x can be equal to is 10 power 80. Yeah. So 8, 1e e 80. So while x is smaller than or equal to range, what we will do is, and also I equals 2. If, but there would also be a overflow at some point, because just the range is just too much. So you also have to take care of the overflow. Let's do this like randomly. Then we'll run a loop for int I equals 1, I less than, say, factorial 25, I plus plus, right? F multiplied by equal to I. C out or std out F include IO string. Right. Shit, we could have done the thing right there. Compile and run. Shit, okay, we are already out of the range. We are already out of the range. 25 factorial seems to be too big. Shit, of course, it will have 15 zeros. 15 factorial is, okay, fine. Yeah, so the fact is that we don't have to do this a lot of a lot. So we can brute force. And yes, we can brute force. We can brute force, yes. Int n, take an n vector of long a5n for long reference x in a, c in x. Yep, that is how the things have been given to us. And our answer in response will start from 2 for int I, for, yeah, for res is already equal to 2. Res smaller than 25, we won't go higher than 25, or yeah, 25 is just too big. Res plus plus. If, yes, and internally for int I equals 0, I less than and I plus plus. If there is any number which is not divisible by, or GCD, if GCD, GCD of res and AI equals 1, then we will say bool then equals false, and we will say done equals true. Rest is our answer, and if done, then break, and here see out rest. That should work. That does work, but we cannot submit. That is the problem. Now, this Heba Kaba loves to sleep. Okay, cannot see. Shit. There is an update in shit. My bad. My bad. My bad. Let me fix this. Shit. Shit. I deleted the whole thing. Okay. Shit. That is like way worse. Video capture. No. I guess you guys can hear me, but okay. I don't guess. Okay. Cool. Fit to screen. Okay. You can see the screen at least now. Thank you for reminding me. I'm stupid. Thank you for that. Now this question. Second last in shit. Third last, Kerber has n friends, each standing on a line at position AI, and each of them is in the range 0 to x. N friends standing in a line at AI position. Each of them is in the range. Yes, okay. They all want to come to him. One of his friends is Samat. Is Samat. Then gave him K teleports. Each friend will walk to the nearest teleport, choosing the shortest distance. Once a friend reaches a teleport Kava and the friend can instantly meet. Kava is so tired that he will be sleeping while his friends are walking towards him. Now he wants to choose K teleport positions so that their positions are distinct, so that their positions of the teleports are distinct and lie within the range 0 to x in order to maximize the time it takes for the first friend who reaches a teleport to reach it. Assume that friends move at the same speed. Since Kava isn't good at calculating, so choose K teleporting positions. Okay. Okay, three integers on the first line. X is the range, K is the number of teleports, and N is the number of friends. N and K are not related, but X is always greater than K minus 1. K, and then there is the position of all the friends and K teleports. We have to decide, and X is the range. Okay, we have to return the positions of the teleports. So I guess since we have a number line, yeah, we have a number line, and let's say there are friends randomly scattered, right? And what we want is to put teleports in these distances in the middle or till the end, right? Right here. And yeah, the only the answer depends on distances. Yeah, the answer depends on distances. We will take the greatest distance and start adding telescopes here or teleports here. And when we do add a teleport, this distance divides into two new distances. This and this. This is position of one teleport. That is nice. And yeah, we can have a vector response size 0 to x minus 1. And that is nice. We will just calculate all of these distances. How? We can keep a pair. Yeah, we can keep not a pair, we can use a map actually. We can use a map where the key would be the distance, like this distance, and the value would be pairs. Now we can keep a set. We can keep a multi-set. Multi-set would be nice. We can keep a multi-set of pairs where the first value would be the key and the second value would be uh, of pair. Shit, the second value would be a pair which has the starting and the ending index of the thing. Yes, shit. Okay, we can do that. We have n, k, and x. Okay, we can do this. That is nice. Let's see. In n, k, and x. Taken n, taken k, and taken x. And now, okay, on the next line, we have positions for the friends. Vector n vector VCTOR vector in E size n, okay, for in reference x and a take in x, okay, cool. And okay, then we will create a multiset of pair where the first value is the distance and what are the limitations. X can be 10 power 9. 10 power 9, yes. Should we cannot 10 power 9, okay, 10 power 9 is doable. Okay, we can do this. 10 power 9 would be X. The distance will be in integers. And then the second value would be a pair of integers where the first value is the starting value and the second value is the ending value. We will call this multiple. Multiset and okay. Now for int I equals 0, I less than n, I plus plus, int L equals 0. The last time we saw something, right? And okay, now multi-set or ms or insert. The distance is ai. Wait, is this thing sorted? Nope, this is not sorted, so we will have to sort this. Wait, my bad. Yep. Yes, you will have to sort this after getting so sort a dot begin and a dot end. So first thing is ai minus L. The last time we saw our friend. That is the first value, and the second value is a pair itself, where the left value is the starting value L and the current value AI. Right. Distance and starting value and ending value and L equals AI. Okay, and in our answer, we will have a set of integers would be our answer. Now, while A exists, what we'll do is we need to find the biggest distance possible, right? Yeah. Auto IT equals ms dot n and minus minus. This iterator is pointing to the one which has the biggest distance. And we'll do k minus minus. We are putting in one teleport. And now where would the position be for that new thing? Okay, shit, there has to be okay. Mhm. So we said that we will get two new distances, but the difference between this original one and this new one is that in the original one we were adding things in the middle. We were adding teleports in the middle, but here in the new one we don't want to add teleports in the middle. We will be adding them here. Yeah, that is something. So what we can do instead of this, and also k can be big, right? K can be 10 power 5. So instead of putting teleports by hand one by one, we can take the biggest distance. Okay, it is fine to put teleports one by one by hand. How do we differentiate between these two types of distances? And yo, I guess the screen is now visible. That is fine, but the camera is not visible, uh, which is even finer. guess instead of taking this distance, we can originally store this distance like this, where we can have something. Like, yes, shit, okay. If you have a person here and a person here, and there is this distance, and if this distance is even, the best we can hope for this one, greedily speaking, yeah, if this distance is even, this is like x, x, then we can say this is a distance which we can have, right? That is nice without disturbing the distance for any other person. But if this was not even, if this was odd, then we would have x and space and x. This is one here. And this we can just randomly choose to go with the one on the right or with the one on the left. Does not really matter. That is fine. We can have two distances in this case. One would be x plus 1 and the other one would be x. Nice, we can do this. Okay, cool. So yeah, we have to change this. And this is fine. L initial equals 0 or shit. We don't even have to do this. Yeah, before sorting, we can say A or here plus 2 or here. Yeah, it is fine to have L. Okay. I thought we can add like buffers, a 0% and at the end something, but okay. This is what we have. Wait, shit, we can do that. We can do that. We can do that. We'll say A dot push back 0 and A dot push back X, which is the maximum value. There could be shit. RAM is too much. Okay. 0 to X, 0 and X both are inclusive. Here and now, yes, we'll start from here and we'll go till smaller than A dot size, whatever it is now. Now, the distance right now in this would be, and we will not go from here, we will start from 1. This equals minus AI minus 1. And okay, we will have to add two things into our multiset, ms dot insert and distance divided by 2. Okay, this depends on distance is even or odd. So distance is odd. If distance is odd, then we will do an s dot insert of ms dot insert. We can always do once this divided by 2, that is one distance, and the starting and the ending points for this one. The starting point is ai minus 1, right? And the ending point would be ai minus 1 plus distance by 2. That looks good enough. And yes, how are these ranges? This is inclusive. We can add a portal on this place. And this is should be inclusive. Let's see, we will make this one also inclusive. If we have a person at index, let's say 0, index 0, and then we have a person at index next one, this place that would, let's say, is 4. And we are saying in this, we are not, this is half open. We will not consider this index at 4. We will only consider this one. Okay, 2. And okay. Should, if that is the case, then instead of adding x, we should add x plus 1. 1, 2, 3, right. And okay, we can put a portal here, 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 or here, and sit there, just 3 things in the middle, here, here, and here. So we'll consider this for the left one. Distance is 4. If we divide that by 2, we get this index, which is nice, which is nice. Yes. So in our map, we can say the key would be the distance, and the distance, should it be inclusive or non-inclusive? Shit. And also shit, there is a distinction between these two types of things. Here we would like to add the teleport on the right, but in a range like this, we would like to add the teleport on the left. Yes, there is a distinction. So how do we make that distinction? We can store that in the state on top of the world. That is, it is not that hard. Shit, I'm just messing this up. Okay, we have been given numbers. We just have to find the one in the middle. Yes. If we have a bunch of intervals like this, if you have a bunch of intervals like this, and there are k, okay, we have our k, yes, and then what? We have our k, we would like to put k's in the middle, like that, the portals in the middle, and we would put the portal first of all in the greatest interval, in the middle of the greatest interval, and then at some point you will stop, and then we will keep start to add portals in the next interval. We will stop and start to add portals. Now we can either, first of all, using binary search, find out the best, greatest time for the first person to achieve achievable, would what would that be? Or yes, we could either do that, and then we can start assigning portals. And that seems like really think of like you can see any pattern, not in test case. Nice. As in like binary search and find the best distance possible here. And when we know that, then it is easy to fill these things. Think that is what you meant. And pattern. But shit, this is crazy. This is crazy. There is also this special interval at the start and at the end where we can add things at the end, which is crazy, which is like, yeah, pretty cool, pretty cool. Okay, E, yeah, binary search, it seems like is the solution. Yeah, we will be able to do this with binary search. And we can write some edge case for the intervals which are on the ends. Uh, and shit, I just feel kind of exhausted. You're going in the right direction. There is nothing in the test case. That is nice. I don't know why. I feel a bit exhausted right now. Uh, we did greedy algorithm. We read like CLRS book and shit. I feel like I am making some excuse. We did one subsection of greedy algorithms and we have done just 4 questions and but those 4 questions were not that difficult. Sure. And yes, what is the point? I feel like I'm making an excuse and I want to end the stream right now because I sort of feel exhausted and I feel like there is no point in continuing currently right now. And it would be very nice if I could take a walk and then get back to programming or doing something other than this. And yeah, so yeah, I guess fine, bro. Try after some time. Thank you. Thank you. But the thing is, I feel like I'm making an excuse. But that is fine. That is fine. Yeah, that is okay. Okay. Cool. And that would be the end of today's stream. And thank you for being here. Thank you for being here. I will always show up every day. Does not matter. Bye. Thank you for being here.